in the class of theories that are dominated by melon diagrams. So we discussed that there were 3 different classes of theories, those dominated by cactus diagrams that were like the vector models. Then we had the melon diagrams, the SYK, and in various dimensions and so on. And then we had planar gauge theories, which are dominated by surfaces, planar diagrams. Okay, so everything we said yesterday was very general for any general dimension and any model of that kind. Now we'll discuss some very specific features that are valid for this case, for the SYK model we discussed in the beginning, so for the 0+1 dimensional case. And we'll see that there are some new simplifications because of a certain approximate scaling symmetry that emerges in the infrared. So when we say low energies, what we will mean always will be that if we have the spectrum, so this was a picture of the spectrum. Sorry, the E is in the, yeah. So this is the energy, and this is the number of states or some measure of the density of states as a function of energy. So we can bin it and find the spectrum, and so we'll be focusing on a region here near the end. And so in more detail, we'll be looking at temperatures or times. So if we consider times or temperatures, which are much bigger than 1, so that the theory is strongly coupled. So remember that when this was small, so we could also consider the limit when this is small, that corresponds to the weakly coupled limit. So now we're going to try to study the theory at strong coupling. And one of the nice features of this Larsen limit is that we will be able to see what the theory does when it is very strongly coupled. But not so strong that the coupling is large, but smaller than n for what we are discussing. In particular, notice that if we took beta j to be very, very large, let's say exponential in n, then we would be focusing on just the first state here, right? That would project onto the ground state. We're not taking that limit. One could also study those very long times or very low temperatures, but we're not going to do that now. Okay, they're interesting to study also. Okay. Now, remember that yesterday I mentioned what the g of tau for Euclidean time at temperature beta. So this is tau from 0 to beta. So it had some form which was roughly like this when beta j was large. And we are going to be interested in the conformal limit, which involves times. So Euclidean times also, we're going to study this at times which are large compared to 1 over j. So in particular, we're not going to be focusing on this endpoint because that involves very short Euclidean times. So 2 fermions are inserted at very short times. We're going to be interested in the regime where we are around here. And we'll find the shape of this curve, okay, that we discussed yesterday. But before we find the shape of the curve, let us recall the structure of the equations. I think the gain is too high, so yeah. So yesterday we discussed some equations in this limit. They become so this was an equation in Fourier space, and then we had an equation in real space, which still. Okay, and then we had an equation in real space, which was of the form sigma of t is equal to j squared g cubed of t. Okay, so in general, we could solve these equations, and we will now attempt to solve the equations in the limit that beta is very large. So first we take n to infinity, and then we take beta j very large. And in that limit, we are going to assume that g of t is proportional to to 1 over t to the 2 delta. So it has a scaling ansatz. So we are exploring whether the solution will have a scaling behavior. We already see here that, well, if we had computed this numerically, we would see that it would have a scaling behavior. Historically, it was just people made these ansatz first and check that one can check that this ansatz is a solution, provided delta is a special value. So I'm now going to show you how to do that. So how to put these ansatz into these equations and check that this is a solution. So that also will give us, well, will show us how to solve these equations, right? In a very specific case. So what do we do? So we start with the scaling ansatz. Then from here, using equation number 2, we could calculate sigma, which is would be proportional to 1 over t cubed. So it would be t to the 2 times 3 times delta. Okay. So we just we use this equation. And now we want to replace in this equation. And so we Fourier transform both sides. So we Fourier transform this one. And the Fourier transform of this will be again a power of omega. Omega is the frequency. And we get the power of omega by dimensional analysis, right? So since this is a scaling function, so when we do the Fourier transform, the only energy scale that appears is the frequency. So this has to have the same dimensions. Okay, so that will give us a 2 delta. But of course, this involves an integral d time. So the actual dimensions are 2 delta minus 1. So those are the dimensions of the integral. Okay. And similarly here, we get that sigma of omega is, we use the same formula. So it's omega to the 2 times 3 times delta, all minus 1. Okay. And now we replace this in this equation. But before we replace it and try to impose the equation, we'll make an approximation. So we'll imagine that at low energies, we can neglect this term. And then we'll check that it was correct to neglect it. Okay. So we're going to approximate the first equation by a new equation, which will be minus sigma of omega g of omega equal to 1. Okay. And then we can sort of replace. Yeah. 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 So we're going to make an approximation. So we're going to make a guess, and then we'll check that the guess was correct, right? So first, we're going to guess that this will be bigger than this at low energies. Okay. Now, why could one imagine guessing that? Well, this is the self-energy correction, so which to leading order was proportional to j squared. So you might think that perhaps when the coupling becomes large, effectively, that might become bigger. But it's something that we'll check later. So that the solution we found was self-consistent. So now we insert in this equation, and we have omega. So from this factor, we have 2 times 3 times delta minus 1. Maybe put the minus 1 here. And then from this factor, from that factor, we get plus 2 delta. Okay, and another minus 1, so it becomes a minus 2. Okay, and this whole thing should be proportional to 1. I haven't kept the overall constant in these functions. We can keep the overall constant. And talking about constants, we could be a little more precise here, because here all these functions have a sine of t or sine of omega. Also this one. But this does not affect the arguments we are doing. So. Anyway, so we could do this argument also with the prefactor, so we even determine the prefactor. But here we're only focusing on the omega dependence, so this has some omega dependence and this doesn't. So this whole exponent should be 1. So we can take out a common factor of 2. This becomes a 1 again. And then this becomes 4 delta minus 1. And so we conclude that this ansatz would work if delta is equal to 1/4. Okay. Now, if you ever did a calculation in a non-trivial interacting conformal field theory, you would notice that calculating anomalous dimensions can be difficult, right? So, for example, if you want to compute them in n equal to 4 super-M mills, it took a lot of effort and many years to compute this dimension. But in this model, you can very easily compute it by doing the simple argument. This is an anomalous dimension of an interacting theory. Now we said we would check that indeed we can neglect this. So now that we know that this is a quarter, so this becomes omega to the 3/2, right? So we put here 1/4 minus 1. That's omega to the 1/2, okay? So what we found here is that this behaves like omega to the 1/2. And now we did check that for small frequencies, so we're doing the low energy limit. So for small frequencies, omega to the 1/2 is bigger than omega. Okay? And so we check the assumption we made in the beginning. Okay, good. So this is a scaling solution. Now, in higher dimensional critical systems, for example, the ICM model at a critical point and so on, once you go to a situation where you have a scaling symmetry, you typically also have conformal symmetry. Okay? That comes from the fact that if the trace of the stress tensor is 0, then you can have invariance also under reparametrizations, which are conformal Killing vectors. Anyway, so in this case, you might wonder whether this invariance could perhaps is also extended to conformal invariance. Now, in 0 plus 1 dimensions, saying that the stress tensor is 0, there is only one component for the stress tensor, which is essentially the Hamiltonian. So this is like saying like the Hamiltonian is 0. And so we expect invariance under all reparametrizations. Okay? So you might wonder whether we have a reparametrization invariance. So question mark, do we have or do we not have this reparametrization invariance? Okay, so in order to explore whether we do have it or not, we can, it's convenient to sort of rewrite these equations a little bit. And in particular, we're going to rewrite the low energy approximation to the equations in position space, or more precisely in time space. So we have that the equation here, if we think of this, fundamentally these variables were functions of two variables. So t, well, let me say integral over t prime, sigma of t, t prime, g of t prime, t double prime, equal to delta of t minus t double prime. So that's the equivalent equation here, right? So in Fourier space, it becomes that equation. And then we had, of course, the other equation, which we can just write it as a function of the two times. That's the equation we had the other day. So t double prime or t prime equal to g t prime. Okay. Now, one can check that if we replace g of t and t prime. Yes, please. Ah, yes. Mm-hmm. If we replace g of t and t prime as f of t, so given a g, we are going to construct a family of new g's, which are parametrized by a function f, which will be this reparametrization. Let me call it t1 and t2 so that we don't make g of f of t1, f of t2. Okay, let's imagine that we had some function g such that as a function of the two arguments was a solution of these equations. We had a function g and sigma, which was a solution. And now we define a gf and a, so here with a delta, and a g sigma, a sigma f, which is the same equation, but here we have 3 delta and then sigma, okay? So if we redefine them this way, the question is whether they are also solutions of this equation, okay? And you can check that this is indeed the case. So I guess for this equation is kind of obvious because this cube is consistent. And in this equation, one thing we need to check is that here when we do this integral over t prime, we can change variables to make it into an integral over f. Okay? And it will work because the total dimension of this is 3 delta, and of this is 1 delta, and together gives 4 delta. But that's precisely what you need to cancel here, the dt, and that gives then something invariant. Yes?
So this function f is arbitrary?
The function f is arbitrary, yeah. So the conclusion of this is that if we do this reparametrization is a symmetry of the low energy equation. So if we had a solution, then we generate a new solution by doing this reparametrization. Okay. Okay, so we have that as a, notice it's only a symmetry of the low energy equations, only of these equations. If we included this term, then it would not be a symmetry anymore. Okay, so we're only checking that it's a symmetry at low energies. And also you can view it as a symmetry of the action we wrote the other day. If you drop there was a dt term in the action. If we drop that term, we also find that it's a symmetry of the action. Okay. Now, so this is a symmetry of the equations. So symmetry of equations. Now, imagine we started with the function g that we wrote over there, which was sine of t12 over t1 minus t2. So t12 is the same as t1 minus t2 to the 2 delta. And we apply this reparametrization, right? So we'll get a new function, which will be, well, up to that sign. Well, there will be a sign also, sign of t1 minus t2. We are going to assume that the reparametrizations are always monotonic. So they're always some increasing function. So they don't go back and forth in time, okay? So that the sign of f1 minus f2 is the same as the sign of t1 minus t2. So f prime is 0. And then we have f prime of t1, f prime of t2. I'm just being more explicit what this formula means. So if we get any f, starting from the solution we already found, we can generate a new solution, which is this one, right? Here to the 2 delta, okay? To the delta, sorry, not to delta. So that's this function. Okay, that's simply we apply this formula so that you see in an explicit case how the formula works. Now, in general, this expression as a function of time, for if f is a very general function, it will be different than this expression. Okay. However, if f is an SL2R transformation, so a transformation, so if f is an SL2R transformation, then there are some f's for which this actually gives the same function. And for example, imagine that f was simply a rescaling of time, right? If f was simply a rescaling of time, then we would get a constant here. Let's say f is alpha t, f of t. So then we get alpha here in the numerator, and we also get a factor of alpha here in the denominator, and the powers are such that they cancel. Okay, now,
very basic
yes,
question.
please.
How do I think of the omega term if the function is not a function of the difference of time?
Yes, so so the full equations here would be this, and then here there would be a dt1 g of t1 g of t t double prime. Okay, so that would be the equation. So that's how it looks in the equation. And more generally, you could think of this as when you go from Fourier transform to position space, you should think of this dt as, you can think of the whole thing as a convolution between dt of a function which is a function of t1 and t2, which is dt times delta of t minus t prime, okay, minus sigma of t prime, all of this convolution with G. Okay. So if you, so you can write it uniformly more or less this way. So when we were writing it before in the previous lectures, we were ignoring this delta of t minus t prime. So it's a little perhaps more clear if we write it explicitly. Okay, so we have, let's imagine we're in Euclidean space, so that time, let's say, is periodic. Well, before doing that, let's notice that we can take an f. Let's pick this particular f, which is tangent of phi tau over beta. Okay. Now, why did I pick this f? Okay. This f was picked so that we map the line to a circle, right? And it has the feature that if we put this f into, well, we could also have chosen an f which was e to the 2 pi I tau over beta. So that's another possible f we could have chosen. Of course, this has some I, but if we put either of these f's in that expression, then we find that G becomes proportional to 1 over beta sine pi tau 1 minus tau 2 over beta, okay, to the 2 delta. So these f's have the feature that they give back a function which is a function of just the difference between the two times, and it's a function that has the right periodicity to be the solution at finite temperature, okay, solution when the theory is on the circle. Now, we could have put the theory on the circle from the very beginning and said that, well, our ansatz for a scale invariant solution will be this one. And this solution indeed has the sort of conformal symmetries you would expect for a circle, for the thermal circle. But we can view it as a special case of what we are discussing over there, where given a solution, we find another solution by a reparametrization. You can view that as an application of what we discussed over there to generate a new solution. And this new solution makes sense when tau is periodic and has period beta. Okay? So this is the finite temperature solution. And now we could repeat the discussion and say, well, we are just doing a reparametrization of these solutions, and now we can think of the problem in Euclidean time, and we can further reparametrize tau, right? As we can go from tau to some function phi of tau, okay? And so these are mappings from the circle to a circle, right? And sometimes called the diffeomorphisms of S1. But not all diffeomorphisms of S1 give us different G's, only the ones which are not an SL2R transformation. In other words, so if we use those variables over here, if we have two functions which differ by an SL2R, so if we have, let's say, f on one hand, or we have, let's say, f tilde, which is a f plus b over c f plus d, and ad minus bc is 1, okay? So for such a new function, the g we get from this one and the g we get from this one will be exactly the same one. And the reason is that this original expression is invariant under a reparameterization of this time, which is of this form, okay? So a t plus b over c t plus d. So the space of inequivalent functions is diffeomorphisms of S1 divided by S2, by SL2, sorry. What we are finding is that we have a problem that has some symmetry, and the symmetry is broken, is spontaneously broken by this solution, but it's not completely broken, it's just broken to diffeomorphisms of S1 divided by SL2. Okay, so that's the space of Goldstone bosons. Okay, so are there any questions? So the take-home message from this is that we started with some system that was just a bunch of fermions or qubits, if you wish, and more precisely fermions. We go to low energies. It develops the equations and action, develop an approximate reparametrization symmetry, which the solution, and this symmetry is broken explicitly by the solution. Okay? So, sorry, it's not broken explicitly. It's broken, the technical term is spontaneously. It's broken spontaneously in the sense that we had equations that had a symmetry, and the solution doesn't have a symmetry. Okay, okay, very good. So now, I should say a few more, one extra, well, the side comment about the this thermal correlator is the following. So this is the thermal correlator in Euclidean signature, and from here we can get the correlator in Lorentzian signature. So we get from here that in Lorentzian, G Lorentzian, as a function of Lorentzian time, will be of the form 1 over beta, and this becomes Hein hyperbolic of pi T1 minus, well, tau Lorentzian. Well, let me call it T again. T1, T12 divided by beta, okay? To delta. And importantly, when we do this, there is an I here, okay? That appears when we go from Euclidean time to Lorentzian time. I mean, we just put t equal to I tau. Well, it's tau equal to IT, right? We get an I. And then this implies, because it's raised to the 2 delta, that this Lorentzian correlator will have both a real and imaginary parts. Okay, so we get these two features. Also, this Lorentzian correlator is such that it decays exponentially at late times with a rate. So we can, well, we expand this for large times, and then we find that it goes like e to the minus 2 delta t over beta, right? This is the behavior for very large times. So it decays exponentially, right? So it means that we can think of this 2-point function, Lorentzian time, as perturbing the system at time equal to 0, and then we watch what happened with that operator. So we perturb the system with adding fermion number 1 at time equal to 0. So if you look at fermion 1 again at some later time, well, the expectation value will be non-zero given by this. But as you go to later and later times, that expectation value decays exponentially, so it looks more and more like the thermal expectation value of a psi 1, which is 0, right, in the thermal ensemble. Yeah.
So this is the general solution, the
Yes.
solution?
No. Well, yeah, the most general solution. No, there could be other solutions. Yeah, we don't know what all the solutions are.
So this is one solution that does not have a symmetry, right?
Yeah, so this is the solution that you get by let's say you solve the problem, let's say at high energies, and then you go to low energies, you land on this solution. Okay, so this is the correct solution at low energies. This one here, or for a thermal circle like that one over there. And this system of equations might have other solutions. But what we're emphasizing here is that first, we believe that this is the solution with lowest action. And second, that this solution is continuously connected to a family of other solutions given by this F. Okay, so we have like a manifold of Boston bosons. It's a complicated equation. There might be other solutions. Yeah. Yes, so all solutions of these equations should have this feature that they would come in a manifold. Exactly what the manifold is, it depends on whether the solution had the SL2R symmetry or not, right? So it might be that the solution doesn't have the SL2R symmetry, then it's bigger. Yeah.
Can you interpret this correlation function where times is coming from some kind of effective numerical interaction with fermionic equidistance?
Well, this is just the time of the, well, I mean, we are calculating something in Lorentzian time. So what this is the expectation value. So let me be more clear on what this is. So this is the expectation value in Lorentzian time of the fermion, let's say L, fermion 1, let's say, fermion 1, time t1 and time t2. Okay. So that's what this is. And more explicitly, we have a factor of e to the minus beta h, and then trace, right? And if we want to be even more explicit, we have 0 here, e to the, so factors e to the t12h, and so on, blah, blah, blah. Okay. So it's, that's what it is. So it's now, how do we calculate it is another question, right? So the Schwinger-Keldysh is a technique for calculating this in perturbation theory, where in perturbation theory, it's convenient to, well, to expand the Lagrangian and have time order the contours and so on. And then you draw a contour which, roughly speaking, goes around in Euclidean time by an amount of order beta. And then you continue in Lorentzian signature, and then you go back in Lorentzian signature. And then in this contour, you insert one operator here and another operator here. So that's a technique for calculating this in perturbation theory. There's no further physical significance to this contour other than it's computing this quantity.
But you're putting here some sources which are
Yeah, the sources here, yeah, of course, we have, in order to compute this, we insert fermionic operators, one fermionic operator here, another over there. Yeah. That's what we do. I mean, we said in the first lecture, we said how these fermions, you could realize them in terms of sigma matrices. You could put this in a computer for any small value of n. You can just compute this explicitly. It's not anything. You don't need a Schwinger-Keldysh or anything to. You can just in the computer write this value, diagonalize the Hamiltonian, and then compute this quantity in this.
I was just wondering because conceptually, when you have this kind of contours,
yes.
More or less what expect in this limit.
Yes. Mm-hmm. Yeah. Well, this is the computation. We'll later discuss some other computations with this in different orders, and then it's given by a more complicated contour. Yeah. Okay. So yeah, one other point about the thermal correlator is that we had discussed before, I think a few times already, this form of the g of t as a function of time. So this function is given an approximation which diverges here at time equal to 0 and beta, and is correctly approximating this function when beta j is much bigger than 1. Okay? So the plot of this sign is this part here, and here it diverges, so it differs from the correct solution at short times. Okay? Is that clear? This you can check by simply calculating the solution numerically, and then you plot the two functions, and you see this feature. Okay? So it's not a hypothesis. It's just a statement about the solution. Good.
So, I have a naive question.
Yeah.
Because this reparameterization invariance,
Yeah.
when you set up the problem numerically, how do you know that the solution is unique?
Yeah, so when you set up the problem numerically, you have to choose a j and a beta, right? So you cannot do it for beta. Well, I don't know how to. If beta is infinite, then you would have also another infrared divergence from. But so normally you would do this for finite beta, and then there is some finite value, and when you do that, you find a unique solution. We'll discuss. I think the answer to your question will become a little more clear later, because, well, maybe I should just say it right now. So the idea that we have these Goldstone bosons, it's problematic because we would have an infinite number of solutions. And these are solutions of the, let's say, Euclidean action, so we in principle have to integrate over all of these solutions. So it would give us a divergence in the path integral. But the original problem was finite dimensional and so on, so it could have no divergence. And in fact, what happens is that this symmetry is also explicitly broken. So it's broken explicitly by some term in the Lagrangian that we'll discuss in detail in a second. And that selects a unique solution, which is which would be that one or this one for the low temperature.
Which is the omega there.
Yeah, it's not quite the omega, because the omega is a property of it appears at very short distances, but it's basically the effect of this term propagated all the way to the low energy solution. Yeah. So the perturbation. So omega is like a perturbation of this system at very short distances, and then you have to and then you have to see what the effect of this is at longer distances. We only know the solution is scale invariant at longer distances. So the delta is something that will affect whatever is going on here. And then you need to propagate this to longer distances and see what effect it has on the effective action that we'll discuss in a second. Fortunately, we can say what the action should be without solving this problem completely. I mean, solving it explicitly, I mean. Yeah.
So you get some redundancy because of the parameterization. And do you have a level of codes because of the redundancies in the particular?
No, you would. I'll discuss this in more detail in a second. I will discuss this path integral in detail in more. If I didn't answer your question, please ask it again. I want to make now a point about the exponential decay of the two-point function. So we saw that it was exponentially decaying, and I just want to make a general point about the exponential decay of two-point functions. In a system with a finite number of degrees of freedom or finite entropy, you could not have that the two-point function decays completely. So you cannot start from a thermal state and then perturb it and then decay back to the thermal state. You should this two-point function should have terms that do not decay, that remain, let's say, maybe fluctuate and so on, but whose the square of the long-term average is non-zero. So you can argue this by starting from this correlator for a system with finite number of degrees of freedom, taking the square and doing the long-time average, and then you find that if you have a finite system, it cannot be zero. And okay, but this is not a contradiction, because this calculation is only valid when these times divided by beta are much more than n, we said. Okay? In fact, this computation, if the time is bigger than n, can also be done by computing things using the Schwarzian theory, more sophisticated than what we have done. So quantum corrections of the Schwarzian theory become important. Maybe I'll mention later how it's done. But so in this problem, we can easily compute this up to times which are, let's say, exponential in n. And then when you reach times exponential in n, you should really see the discreteness of the energies. And recently, there's been some progress also understanding how you get that regime from gravity and so on, or from this type of action. Okay, so now this was a side comment. We go back to these classical equations we are solving, so the leading order in large n. And we said that we found the solution, could be either that or this finite temperature one. And then we can put it back into the action. And that enables us to calculate the partition function. So we can put that, we can have the log of c. So that is given times n times the action we had yesterday, evaluated in this solution. Remember the action, so we had, trace log of sigma. Here there was a dt minus sigma, but we are neglecting the dt. And then there were some terms that had a g sigma and then g c to the 4th, let's say. Okay. So it's a simple matter to put this into this action. So let's say, for example, here we get something that goes like 1 over sine. Let me set beta equal to 2 pi, so make like this. Well, no, let me not do that. Pi t over beta, right? Squared. So we had it to the 2 delta. Delta is 4. Delta is 1/4. Raise it to the 4th power. We get this term. We get something similar for here. From here, these two don't cancel. We get this. Okay. So there's a factor of beta, and then there is an integral dt. There's a factor of beta here. One factor of beta came from one of the time integrals, and this is the second time integral. So when we do this, from this term, we get purely a UV divergence when t is equal to 0. So when t is equal to 0, this goes like 1 over t squared. We get infinity. So you might be worried that we get in infinity. But remember that this solution is only valid for large times, and for short times, there will be some other solution. And so effectively, that solution will cut this off at some small epsilon. And when you do that and the dust settles, so that small epsilon term will give you this small epsilon will be of order 1 over j, and this whole term will give us something of the form beta times j times some number that we cannot compute using these approximations. Okay, so that's one term we get. From these other terms, we get also divergences, but we also get a constant term. So I will not discuss how to compute it. There are some tricks to compute these determinants I will not discuss. But the final point I want to say is that there is a term that goes like beta j times some number. So this really is a divergent term that is not calculable within the low energy theory. And then there is some term we can call S0, which depends on this number 4. Sometimes we can call it S0 of delta. And that's what we can calculate using the conformal theory. Okay. So that's what we get for logarithm of z. Okay. Now, this first term can be viewed as the ground state energy, so the energy. Right? So if we look at this and we say, well, what kind of system do we have? Well, we have some system that has some ground state energy, so we could, of course, subtract it and ignore it. And then we have something that is sometimes called the ground state entropy. So it looks like we have many, naively we would say that we have many degenerate states, all e to the s of them. Now, remember the picture we had for the spectrum. The picture we had for the spectrum was something like this, right? Now, the ground state energy, so would be this value. So here we said there was a value of minus n times j times some number. And this number should be the same as this number. Okay? It's not calculable within the low energy theory, but you could in principle calculate it. But it's not interesting because it's just a moral subtraction you can do. But this it's not a constant here. I mean, this goes to 0. So the density of states goes to 0. And one can see exactly what the density of states is. We'll not discuss it too much. Let's say it goes to 0. But you might wonder about the emergence of this ground state entropy. And so the way to think about the ground state entropy is that the density of states is going to be the ground state entropy appears as an overall factor in the density of states. And then the density of states could be times n. So S0 is a function independent of n, and then it's proportional to n. And here there could be some function f of energy, let's say e minus E0, rising function which that's at 0 and grows, but that is independent of n. So this is consistent with the large n limit, and is consistent with this form of the entropy, right? Of the free energy. So we have this constant to leading order in n. That's somehow saying that when we write the density of states, we have this leading order in n piece, which is a constant, and then there could be a subleading order in n, which is dependent on energy. Okay, and that's then the form that we can have here. Okay. Okay. So So that's one important point. So the fact that we get ground state entropy at leading order in n does not imply an exact degeneracy, right? So we could have a perfectly smooth, let's say, density of states that goes to 0, and nevertheless get this ground state entropy. Okay, is that clear? Now this, yeah. Okay. No, yeah.
It's not clear to me how do you get the density of states?
Yeah, it should not be clear. So I'm just saying what kind of. I haven't told you how you get it. I have. What I meant to explain is that what is a density of this is a density of states that is consistent with the answer. Okay. And it's also consistent with this picture we said before, and I have not explained how to get it. Okay. Yeah. So there are different techniques for getting the density of states in different regions in this diagram. There is a technique for getting it here at low energies that relies on the quantization of the Schwarzian theory that maybe I'll get to a bit later. So for very low energies, we have an expression for this density of states that I'll try to explain how to get it. Yeah. My whole point in explaining this was to explain that a ground state entropy at leading order in n does not imply exact degeneracy. Okay. Now, there were many calculations of black hole entropy, for example, in string theory and so on, that are for black holes in supersymmetric theories. And in those cases, those black holes exist exactly at the lowest energy. So the density of states is different. It's something like this, and then there's a delta function here at the very end. So, but that is not a necessary condition for reproducing properties of black holes, so, such as the ground state entropy. So if we have the Schwarzschild black hole in in the standard model, it's not expected to have exact degeneracies at the extremal limit. Okay, so in fact, so there is this term, and then here you can view this as an expansion in powers of 1 over j. That's the low energy expansion, and then there is one more term here in the low energy expansion that we'll discuss later. We'll discuss later the origin of this term, but let me just point it out right now. So there is a term here in the log of z that is linear in the temperature. So that will give also an entropy which is linear in the temperature. So this is of higher order in the 1 over beta j expansion. I'll explain in a second. Well, I'll explain a bit later how to get this term. Again, it will come from the treatment of the reparametrizations. Now, before getting there, let me just say a few things about this function. Now, the original dimension of the Hilbert space was 2 to the n over 2, okay? So, or e to the n over 2 log 2, okay? So it better be that this thing should be smaller than log 2 over 2, right? Otherwise, we have a problem, okay? And indeed, it is smaller, so you can actually compute this function for a general class of models where we have here a q. And then we find as a function of delta, which is the same as 1 over q, we find that there is some curve here that goes between 1/2 log 2 and 0. So we get 0 for the model with q equal to 2. So this is the delta equal to 1/2. And for delta equal to 1/4, you get some number, okay, which is between 0 and 1/2 log 2. Okay. So if you compute the density of states here near the maximum, you will get something of order this log 2 when 2 log 2. When you go to this low energy regime, you get the overall prefactor, which has a smaller reduced coefficient. Okay. Yeah, and we're plotting this number as 0. Yeah, for different models. This is not for one model. This is for different models that differ in how many fermions we had interacting. Okay, so the purpose of showing you this is first that for delta equal 1/2, which was that simple integrable model we saw in the very beginning, we have 0, and that we have a non-zero answer for the model main model we were discussing. And for this whole range of models, we have something which is smaller than the maximum. Okay, so now let's address a bit more the question that Pedro was asking. So what do we do about these 0 modes? So the space of 0 modes is this space. And we said that in the action, the leading low energy approximation to the action was independent of which of the 0 modes we had. So we write, so this is basically the space of G's. So this is a high dimensional, let me be more precise. So we're trying to compute a path integral, which involves a path integral over G's and sigmas, right? G's and sigmas are functions of 2 variables. We're supposed to be integrating this e to the minus n times the action of G's and sigmas, okay? So now, if we have a situation like the situation we have over there, then we will find, well, there is a minimum of the action, which is, let's say, some particular G0. So we have the action of that G0, so I of G0 and sigma 0. But we can reparameterize this by f, and they all have exactly the same action. So this action is independent of f. Okay.
Before doing that, could I write this integral for n equals 2 or 3?
Yes, yes.
For n, for finite.
Oh, yes, you can write the integral. Yes, it corresponds to doing the disorder average outside the path integral, but yes.
So we know
you can do it.
What the measures mean exactly.
Yes. The measure of this, remember, came from writing a delta function. So this is a flat measure in the space of G's and sigmas. Yeah, this is an explicit integral, and in some cases people have done some computations using this, some more details of the measure. My only point here is that in this big space of G's, this is one direction in the space of G's, this is another direction in the space of G's. Of course, it's an infinite dimensional space, it's a space of functions of 2 variables. There is one point, which is the solution we discussed, 1 over T1 minus T2. So that's one solution. But then there are all these reparametrizations of that solution, and that's some, let's say, subspace of the space of all G's. I drew here as a line, but is, again, an infinite dimensional space, but is smaller dimension than the space of G's. Okay? This is the space of functions of 1 variable, and this is the space of functions of 2 variables, right? Is the distinction clear? This should be crystal clear, okay? So we were supposed to integrate over all of this, and there was a minimum of the action, but we have a whole configuration with the same actions. So imagine this as a landscape that has a long valley, right? A valley with exactly 0 action in the leading approximation. Okay. So that was the action to leading approximation, which is independent of f. But as we said, there are some 1 over j corrections to the action. Well, there are some 1 over j to some power corrections to the action, some suppressed corrections that will lift this degeneracy and will give us something that breaks this reparameterization symmetry. Okay. Okay, I need to stay far from the blackboard. That breaks the reparameterization symmetry and will put a little potential, a small, shallow potential that will localize the solution here at the minimum, okay, of that potential. So this line is the space of Goldstone. It's a space parameterized by the Goldstone bosons, okay? And what we will do now is try to understand what these terms are that break this symmetry.
the integral that we said that we could compute for small
Yeah.
lines,
Mhm.
that one is exact. I don't need to correct anything, right?
Yeah. That's exactly.
So that I is not the same as that I, or what am I missing?
No, well, okay, so, yeah, okay, fine, sorry. This is an I that depends on J, okay? Well, or beta J, right? And this term is the leading expansion for beta J very large, right? And then there is another term in the expansion for larger, well, for beta J not so large. So this is an expansion in 1 over beta J.
And the dependence on beta J is a bit implicit.
It's very implicit, yeah, it's
the
implicit.
boundary conditions for the
Yes, indeed. Mhm. Yeah. Is that more clear now? Yeah. Yeah. So when we could rewrite this by, so we could pull out the betas and j's here from this expression completely, and they would appear only in this dt. Okay. So that the leading terms don't depend on it at all, and then so that would make it more manifest. Okay, good. So our task now is to understand how the symmetry can be broken. Now, when you have a problem that has a symmetry, sometimes and it's only broken by a little bit, you can classify the possible breaking terms by the same symmetry somehow that you have. And so we'll write the simplest term that we could write down for this, and we're going to use some intuition to say what this to make it plausible. So the first point is that we have these actions that depend on two variables, and recall that the deviation between the conformal answer and the correct answer was present at very short distances, right? So when we drew, for example, the expression of the correlator that looked like this, I drew this many times. It's only for very short times very short relative times that we found the difference. So it's reasonable to think that that even though when we put this into the action, we have these functions which are functions of 2 times, that the terms that actually depend on f will be terms that depend only on 1 time and will be local terms. So will be terms that in the Lagrangian, in this action, so those terms there, will be an integral d time over some Lagrangian, which is a local function of f, f prime, and its derivatives, okay? So this is, I try to make this assumption plausible by saying that we expect that the action might come from the places where the 2 times are close together, right? So for example, there were some terms in the action we wrote that were integrals over 2 times, and when the times are separated, those are perfectly conformal invariant, but when the times are short, the g's are different, and there will be some new correction, and the correction there, then it will be local. We expect it to be a local function of this kind. So we make this assumption. Once we make this assumption, we then notice another point, which is that if we have 2 f's here that differ by this transformation, those 2 f's are describing actually the same point in the space of 0 modes, okay? So they are defining exactly the same g. So if we have, so this is, we are trying to integrate over g's along the valley. The valley is parameterized by f's in this way, but 2 f's that differ by this transformation give exactly the same function, okay? Give exactly the same T1 and T2 dependence. And so the action, whatever it is, has to be invariant under SL2. So this should be SL2 invariant, where the SL2 transformations are the ones we wrote over there. And the simplest action that has these properties is, I should write it here. The simplest action is the so-called Schwarzian action, the Schwarzian derivative of f, sometimes called with a bracket like this. This, just by definition, is equal to f double prime over f prime. It has a somewhat slightly complicated looking expression when you first find it. Now, this is the simplest expression with lowest number of derivatives. That is SL2 invariant. Okay, so that's the idea. And so then we expect that the first term in that action then should be given by this expression, and we'll have some power of j here, which is determined by dimensional analysis. So here we have a net number of two derivatives. We have some derivatives in the numerator and denominator with respect to time. But we have a net number of two. We have one integral over time. So this whole thing has dimension 1. And so we need 1 over j for dimensional analysis. So this power that we didn't know before, the first term has a power which is 1. Okay? And is equal to the Schwarzian action. So now we have here that we have the Schwarzian action. So that's the correction to the action. Now there is an overall n, which was multiplying the whole action. So this correction also has this factor of n. And also there is some alpha s, some constant that we don't know. So there is some number that we don't. This argument doesn't determine what the number is. It only says, well, there should be some independence, and then this number is just some number you need to compute in some other way. Okay. Okay. So that's an argument for this action. I tried to make it plausible. People have given some other arguments for why this action appears. We gave one argument in our paper with Douglas Stanford, where we looked at the 4-point function and the effect of this on the 4-point function and checked it explicitly by computing it in an alternative way. Kitaev and Josephine Su also gave another argument by sort of formalizing a little more this idea that we start in the UV with this DT term and then flowing it to the infrared, and also argued that you should get this action. Okay.
So the reason why you cannot just start and expand it because this decomposition of the space of functions is a bit subtle. And a priori, as you said, so the first line you can write very explicitly, right?
Yes. Yeah. So
why can't I just see this mathematically? Expanding beta j and find what.
Yeah. The problem is that the action itself depends on the solution, right? And it's a non-linear action. And so when you try to expand the leading dependence, you would get something in diversion because it changes the solutions in a way that it diverges near the point where you're near short times. And so you need to really find the full solution near this short time behavior to be able to compute this. And if you wanted to compute that coefficient alpha s, you have to numerically find the solution and then match the coefficient. So somehow go through the whole flow. This is, okay, let me make an analogy in general. So suppose you have a UV quantum field theory that flows to some infrared conformal field theory, right? So in the UV, you might deform the theory by some operator which will turn out to be relevant in the infrared theory, with some coefficient that is, let's say, well-defined in the UV. But in order to know what the coefficient of the relevant operator is in the infrared, you need to solve the whole flow. It's not, there isn't a simple formula in general. Yeah. And this is similar. Okay. So now we can remember that we took a solution f, which was the tangent of pi tau over beta, okay? That gave us the solution for the circle. And so if we take this solution and we insert it here, we get a term, some expression here, which goes, this whole thing goes like 1 over beta. And that's the term that goes like 1 over beta j that I mentioned in the free energy. I mentioned that term before. It's here. We are deriving it. Okay. And that gives, in general, some term in the entropy. So the entropy will be this S0. So it will be an n S0 plus some term that goes, I'm not keeping track of coefficients. There's a factor of 2 relative between that term and this term. But and then this term. This could be written in terms of the temperature. So it's a term linear in temperature for the near extremal entropy, for the entropy at low temperatures. So the fact that we have something linear in T is a consequence of this pattern of symmetry break-in that we discussed, of having the reparametrization symmetry spontaneously and explicitly broken. This whole story that we've discussed has as a consequence this particular power of temperature, right? If we didn't know about this, then we could not have said what the power of J here correcting this action would be, right? So we got this power because of the particular form of this action. Otherwise, in principle, just from general scaling arguments, it could have been any power. Okay. I should say that this form of the entropy is also universal for any near extremal black hole, and we'll understand why that is the case there also. And the reason I went slowly through this whole discussion of reparametrization, symmetry breaking, and so on is because we'll find the same structure in ADS2, in nearly ADS2 gravity. So when we start looking at the near horizon geometry of black holes, we'll find that there is an ADS2 geometry, and that nearly ADS2 geometry has the same pattern of symmetry breaking that this model has. Yeah, I should say that this emphasis on the symmetry breaking and so on is something that Kitaev realized, so that when he introduced the model, and the Schwarzian action and so on, he also pointed out. Okay, and I recommend that. So this whole, everything I think that I've discussed was discussed in some lectures by Kitaev that you can watch in the KITP website. Now, how much time do I have? Negative, no, I have positive.
So normally we need 15 minutes per question.
Okay.
5 minutes and then 15 minutes.
5 minutes, okay. Okay. Okay, so remember that yesterday we talked about the 4-point function. So we can divide it by the 2-point function. The subindices denote the times, so T1, T2, T3, and T4. Okay, is that clear to everyone what this means? Yep. Okay, so we said that we have a 1 plus then a 1 over n correction. And the 1 over n correction came from, had roughly the structure of some kernel divided by some 1 minus some kernel. That was a complicated thing. Now, in the case that we have conformal symmetry or low energy of scaling symmetry, just the global part of the conformal group, let's us write this in a simple way as an integral and a sum of over some the dimensions of some operator, some measure that I won't be writing. And then that kernel just diagonalizes to a simple function of h. So this is just an ordinary function of h. So you can diagonalize completely that kernel that was acting on functions of two variables by using conformal symmetry. I'm not discussing the details, but it's, hopefully it's believable that by using some of the symmetries, the problem might be simpler. And then there is here some function fh of the cross ratios. So this is basically a function closely related to conformal blocks. Now, so that's what you can say just based on conformal symmetry. It turns out that there is in these integrals over intermediate states. So this here we integrate over normalizable states, etc. There is actually one point in this sum where this is actually 0. So this result is actually infinite in the conformal limit. And that infinity reflects the fact that when we do just the conformal analysis, we neglect this. Okay? But then we include this, and by including that, we'll get something finite. But that finite thing, so first of all, this leading term is independent of beta j, so it's just some number. I mean, it's a function, sorry, of T1, T2, T3, and T4 is a function of the cross ratio, but independent of beta and j. But this divergence gets regulated by that action, and we end up with something of the form beta j over n, and then some particular function of T1, T2, T3, and T4, okay, that I'll explain how to calculate in a second. And then plus the same sum and integral that we had here, but now the sum is over an h. It turns out that h equal to 2 is the problem. So if you sum over, it doesn't matter why it's 2 and so on. So, well, if you want, you can ask me in the question period. The point is by removing one of the contributions and treating it separately, we get this large factor. This large factor would come from integrating basically along this valley. So the infinity comes from the path integral along the valley in the 2-point function. And I'll tell you in a second how to compute this, and then we get something finite here. So let me discuss how to compute this. So we're trying to do that path integral we're discussing over there. And we are trying to do the path integral for computing the 4-point function. So the path integral that we are doing, well, maybe I should just come here and so we're trying to do here a path integral dg and d sigma of g12 and g34. Leading order term is just to set the value of the action here, the minimum, the cross here, and that gives the 1. And then we have to integrate over the g's and sigmas. So there are integrals along the orthogonal directions, and those we can use conformal invariance and so on, and they give us essentially all these terms. And then there is the integral along the valley directions. And the integral along the valley directions, if we ignore this term in the action, gives us an infinity. But now we include the term in the action, and we do the integral, let's say, only along the valley directions, which so we will approximate this integral by integrating only over f's this action, e to the n alpha over j Schwarzian action f t, right? And then what we put here is gf of 1, 2, and gf of 3, 4. And gf is the expression written over there. Okay, so we had the expression here for gf at the end of the blackboard. We just put those expressions here, so that's some function of f. And then we do this path integral. That will give us the contribution integrating along the valley. And that would be the dominant contribution at low energies. Okay, so the simplest approximation to that is to take a particular point here and then expand f to quadratic order. And if we do that, then that becomes just a simple Gaussian integral. And that Gaussian integral is what gives us this answer. So this is some explicit function that is not too complicated, but I won't write it down. So it's the result of taking, for example, this time here and expanding it as t plus epsilon of t. And then this action becomes something simple, becomes n alpha over j times the integral of epsilon double prime squared minus epsilon prime squared, some action roughly like this with a minus sign. And by integrating over these epsilons, you get the value we said over there. Okay, good. And in this way, you can calculate a bunch of things. In particular, there is a particular correlator that was interesting. Maybe I'll discuss next time why it is interesting, which is an out-of-time order correlator that has some connection to chaos. But I'll discuss perhaps that. I'll leave that for next time. So let's discuss questions. So, thank you. Yeah. Yeah. So when we do the computation of the path integral, right, there will be some pieces of the path integral that will give an enhanced answer. An enhanced, it will be large because they will receive a large contribution from the integration along the valley, right? Because the integration along the valley is unsuppressed, right? So you can have a large contribution from the valley. And so what we are explaining is how to do that integral along the valley, right? That you can just take the, you can take all functions, well, everything that appears here, and evaluate it along, take this solution, and so what is this valley? This valley consists of taking this solution and reparameterizing it. So it's the space of functions of two variables which have that form, right? They are parameterized by a function of one variable. But then you put those functions anywhere in the observables that you have. So here you have these observables, you put those. So in general, this is a general function of two variables. Now we put those functions. And we do the integral over f. So that gives us the terms that depend non-trivially on j and beta that break conformal symmetry. So all other terms, all integrals perpendicular, they preserve conformal symmetry. They have a different characteristics. And so this path integral gives us the terms that preserve that break conformal invariance. So in particular, you could imagine computing just the partition function. And so the partition function, so we'll have the partition function will have a piece that preserves at very low temperatures, a piece that preserves the conformal symmetry. Well, maybe I explain that next time. But I think it makes sense now. So we can integrate just the Schwarzian action. So we get something here which is S0, and this, so S0, let me call it S0 tilde. So S0 tilde includes the term going like n times S0 and any other quantum corrections that we could have that preserves conformal symmetry. So there will be some corrections, some constant. And then there will be the integral that involves the Schwarzian action. Now it turns out that this is a special action, and you can actually do this path integral exactly. So you can actually do this whole path integral. And the answer turns out to be very simple. So you have a term that goes like 1 over beta j, right? Maybe this alpha s, there are some factors of pi I'm not writing down. This was just simply the classical answer, the answer we also mentioned. Then there is something that looks like a one-loop correction. So we would get this if we were to do the Gaussian integral, just show the integral over epsilons here around the saddle point will give us a determinant, and that determinant evaluates to this quantity. And then there are no further corrections. So all other higher order terms in the expansion in terms of this coupling are not present. And we get this answer. So Douglas Stanford and Ed Witten discussed how to get this using some form of localization. And there were also then other authors getting it in different ways. So there are different ways of getting this. And from this, if we Fourier transform, we do a Laplace transform in beta, we get the density of states that we discussed before. So we get some approximation to the density of states, which, sorry, here I forgot the S to the S0 tilde. So this is something we cannot easily compute, or we can compute the leading order in n, for example. But here we can have this whole beta j dependence that we can compute. So this is an example of a computation where there is a piece that is conformal invariant that, well, we will need the details of the SYK model and so on to compute. So this will depend, for example, on Q and so on. And then there is the other piece that breaks the conformal symmetry, but can be computed explicitly because we know exactly how the symmetry is broken.
Okay, just maybe could you give an overall picture, because I'm a bit lost, so where we are going?
Yeah, where we are going.
Thanks.
Let me say what the first lecture was about. So, as I said, the first lecture was about a new type of large limit that is all. This lecture is about taking a quantum mechanical system that develops a scaling symmetry at low energies. And Then, in this particular quantum mechanical system, we found that when you develop a scaling symmetry, you also have this pattern of reparametrization symmetry and so on. We discussed more or less how it arises fairly explicitly in the context of this SYK model. But we expect this to be very general. We expect it to be true for any quantum mechanical system that develops, any large-N quantum mechanical system that develops scaling symmetry. And in fact, we'll see that even for black holes it's true. Okay. This pattern involving the Fs and so on, not all the details, but the general pattern of symmetry breaking will be the same. We'll see, and we see what the F is in the black hole case and so on. I tried to explain that this pattern of symmetries determine the form of the low energy action. That was the Schwarzian action. So one of the points of this lecture was to derive the Schwarzian action. So first point was to point out the existence of a particular direction in the space of functions, in the integration space where we're doing the path integral, a particular direction that is special, that's parameterized by F, that's associated to an almost symmetry. And then we derived that there was a particular action along this valley, let's say, along this subspace parameterized by F. And the action is basically determined by the symmetry itself, by the pattern of symmetry breaking. And then we discussed at the very end how to do some specific computations with it. So I showed you two computations. One was the computation of calculating the free energy that gave us the term that went like this in the partition function. And the second I discussed maybe too quickly, was the contribution to the 4-point function. I'll perhaps discuss it in more detail next time.
But the role of SYK, it's just one example for universality class of theories.
Yeah. So this is in the space of theories with that particular of melon diagrams. This is one particular example.
Okay.
But it's perhaps one of the most interesting examples.
I see.
Yeah.
Thank you.
It is, let me say it this way, what I've discussed here is special because it allows you to see something that we see easily in black holes, and we've seen for a long time in black holes, in extremal black holes, and we can derive it fairly directly from the quantum system. That is what we were discussing today, and that's the main interest. That's why it is. That's basically why Kitaev introduced his model, because he was trying to understand the connection between these quantum mechanical systems and black holes. And I think it's the most interesting example of this type of melon type models. I mean, maybe in the future people will do other things with melon diagrams that are also interesting. I mean, there are other results that have been obtained within these models dominated by melon diagrams, but are results which are, it's an exactly solvable theory, so there are many things you can do. But, you can analyze conformal field theories and compute anomalous dimensions and things like this. But, we can also compute them in some other theories, so it's not as new. This is perhaps the thing that is conceptually newer that you can do with these models that you cannot do with other models. You cannot solve them explicitly. There are many models that are supposed to have an ADS2, they are dual to ADS2 black holes, but they are more complicated. They are large engaged theories, and they're difficult to analyze. They should also have this feature. But it's harder to go from the microscopic theory directly to the feature. While in this toy model, you can go directly to the feature, to this feature.
So does this, now that you have a large limit and also a strongly coupled theory and also conformal symmetry, does it have like an Einstein dual?
The question was whether it has an Einstein gravity dual?
Yes.
Yeah, so the belief is that it doesn't. So
it doesn't?
Yeah. And the reason is that when you compute this 4-point function, you can do an operator product expansion of these operators. Mm-hmm. You seem to find, you do find a bunch of operators in this operator product expansions that you can interpret as operators with higher spin. Spin in 2 dimensions is a slightly difficult quantity to define, but if you define it by saying how they would look like, how they would contribute naively to the chaos correlator, then that's one definition. Then there would be higher spin operators in that sense. And when you expand this, you find lots of, the dimensions of those operators are of order 1. The anomalous dimensions are of order 1. While for an Einstein gravity dual, we expect all those dimensions to be very large.
Okay, so from the point of view of this work by Polchinski, Hemskerk, where you can list all properties, what goes wrong, or what is missing in this case?
Well, the idea is that any theory where all the higher spin operators have large dimensions should be dual to Einstein gravity, right? But this is not one of those cases. I've said that here, when you find which operators you find operators with low dimensions.
So it doesn't have like this sparse spectrum?
Yeah, that's right. It doesn't have, well, sometimes this is called the gap in the spectrum, the idea that in the spectrum of operators, the ones with higher spin have large energies.
Yeah, so that you can like identify the gravity.
Yeah, that's right. So that basically the fundamental particles that you have in your theory, either they are the spin 2 graviton or lower spin particles, and all the higher spin particles are very heavy.
Okay.
So that's believed to be perhaps a sufficient condition. It's certainly a necessary condition for the validity of Einstein gravity. And that necessary condition we don't have here.
Okay.
So what we'll see is that, I mean, the picture is that we have some complicated, I don't know, gravity, whatever theory in ADS2. But ADS2 will be special because ADS2, it's not exactly ADS2, it's nearly ADS2, and the symmetry is broken in a controlled way, basically by a pattern very similar to what we discussed here. It will turn out to be identical to what we discussed here when you look at it in the right way. And so even despite the fact that we don't have perhaps you have a string theory or some complicated gravity theory, this pattern of symmetry breaking will be the same as the one you have in Einstein gravity. The pattern of symmetry breaking is universal for Einstein gravity, non-Einstein gravity, and SYK, etc. So, in fact, we think, well, at least I think it's reasonable to conjecture that this pattern is present for any quantum mechanical system with an emergent scaling symmetry in infrared.
Thank you.
Another question? So halfway through, you said something about these density plots with energies having a delta spike for certain black holes in the beginning.
Yes, yes.
I didn't really follow that, but it sounded interesting. Could you maybe say something more about it?
Yes. So in this model, the density of states goes to 0. So you can get that. You can compute this and do the Laplace transform and get the density of states. Actually, it goes like sine hyperbolic. I don't remember the prefactors, square root of E, or E minus E0. So that's near the endpoint, right? Some factors that depend on J, etc., and N. So that's how this behaves. That's based on this. Now we'll see that there is a close correspondence between these systems with emergent. Let me say it differently. There is another system that has an emergent scaling symmetry, which are near extremal black holes, for a reason we'll see next time. So these are particular charged black holes, and when you look at them at very low energies, very low temperatures, you go very close to extremality, they also develop a scaling symmetry. And those black holes have a finite entropy at very low energies. And there are some black holes of this kind that have been studied in the context of string theory, very supersymmetric theories, so theories that have extra symmetries beyond the ones we discussed here. And in those examples, you can make an argument that, at least in those theories, the extremal entropy of black holes correspond to exact degeneracies of the quantum states that are described in these black holes. And so in those cases, what you expect is that there is a delta function here at very low energies with exactly the general states with an amount which is proportional to the extremal entropy. Yeah, so that's... and even in the SYK context, you can find some SYK-like models which have this feature. So if you take... there's a supersymmetric version of the SYK model, and if you do that, then you find this kind of spectrum. But this is only interesting if you want to connect to what was done before for black holes. So all I'm saying is that if you have black holes in a theory, let's say, which is not supersymmetric, which is the standard model, for example, you don't expect exact degeneracy. You have a ground state entropy that you can calculate using the Bekenstein-Hawking formula. But the ground state entropy does not imply an exact degeneracy of the dual quantum states. This is the point I wanted to make. Yeah. Is related to? I couldn't hear.
Speak louder or wait until the microphone.
Louder with the microphone.
So this Schwarzian action is related to the Yakif-Teitelboy action?
Yes, we'll see that next time.
Okay.
Any more?
Maybe tonight.
Yeah.
You mentioned that there was a simple deformation of this model that did not decay as a power law, but as an exponential decay. Right? Is it true?
No, I don't think so. Sorry. We are talking about the Euclidean correlators. Yeah. So there is so this is a model that has this conformal symmetry in the infrared. So that you can consider a model that, let's say, contains a mass term, roughly speaking, and then at then at very low energies, the system has a gap, so it's a mass gap. So the correlators will, at long times, they will decay exponentially due to the presence of this mass gap.
Is it true that in that case, this subtleties, then you would not need to worry about this subtleties in that case?
Well, at very long times you will not have to worry, but I mean in some cases it's actually useful to use this to solve the model. So okay, so this looks like a subtlety. Okay, looks okay. Maybe it looks like a subtlety and a thing that is a little bothersome and so on. But it's actually a big asset because it allows you to solve these G and sigma equations in situations that you would not have been able to solve them. Because you might go to regimes where you can, for example, perturb this model by adding some other term to the Lagrangian that is small, right? And then if you do that, then the dominant contribution will be it will change the solution to a solution another point that is in another point along this valley, right? So with this Schwarzian, the lowest point is this one. But if you add some other term, you might displace this by a big amount along the valley, but by a small amount in the orthogonal directions. And so you can find a new solution of a related model. And so, yeah, you should think, yeah, this whole discussion of the Schwarzian is not at all a nuisance, or it's actually a big asset and it has consequences that explain physical properties of the model.
Okay, so we meet at 2:45 for the next lecture of Juan. So I forgot to mention, if people want to buy T-shirts, you can get with our secretary.
do that. say that you're adding these Olsen modes in order to make the theory local? Because from the starting knowledge trick point of view, you have an integral which has local interaction.
So the original model was local. The original model was local. The formulation in terms of the key and sigma variables was not local, right? But the final physics should be local. It so happens because of the pattern of symmetry breaking. Well, the reason we got the local action for F